Hello all, this is the Pencrest High School AP Physics C video series. This is video 2A, the Newton's Laws Introduction. So, there's a lot of good news concerning Newton's laws. The first bit of good news is that they haven't changed. So, Newton's laws have been around obviously since the Renaissance, and we're still going to be looking at, for the most part, sigma F equals ma. But before we get into that, it would be a good idea for you to revisit the ideas of how to draw a free body diagram, the different types of forces that we run across, Fn, Fg, contact forces, tension forces, friction forces, how to take these forces and use a free body diagram to write a force equation, how to apply that concept to multiple objects like an Atwood machine or a cart and hanging mass system with ramps and pulleys and ropes or cables. We will run across all of these concepts this year. Would probably be a good idea, if necessary, to look either at your old copy of the Blue Book or even the old video series. You may find it to your advantage to play the videos at 2 times speed to get through them more quickly. So the quick summary of the actual laws themselves. The first law, also called the law of inertia, is sigma F equals 0. If you recall, this is the one that starts with an object at rest tends to stay at rest. An object in motion tends to stay in motion. We consolidated that statement into a simple version where if the object is if the forces on the object are balanced or canceling out, that means that the object will not accelerate. By canceling out or by balancing, that of course means that the vector sum of the forces would equal 0. The second law, of course, is the more generic version, or the more generally applicable version. Sigma F equals ma. This applies when the forces do not cancel. So when we add them up in a vector sense, we add them up and we get a net force, a non-zero net force. That non-zero net force is a vector. That means it has a direction. And whatever the direction of the net force is, that will also be the direction of the acceleration. So that sigma F equals ma is a vector equation. And the net force and the acceleration will have the same direction. The third one, of course, is the action-reaction. The force on 1 due to object 2 is equal to the negative of the force on 2 due to object 1. More generally applicable to systems in which there are 2 objects. Once again, like the cart mass system or the Atwood machine, or the contact force when you're pushing 2 objects. We will see other new types of examples of applications of Newton's third law this year. So there is some new content. We're going to look at how our 3-dimensional IJK notation, when we look at 3-dimensional vectors, of course, force is a vector, so it could be represented in IJK notation. So we'll see that. We will also see forces that change over time. So we're familiar at this point with changing acceleration. We called it the jerk term or the t cubed term in the generic position formula. We're going to see that in the event that the force changes over time, that would of course imply, because sigma f equals ma, that would imply that the acceleration also changes over time. So we will see examples of that. We will also finally take a look at how wind resistance or air resistance actually works, how it actually works mathematically in a force equation. So we'll see that also. One thing that we want to take a look at, the link between Newton's laws and kinematics, of course, is the acceleration, because it appears in both of them. So when we look at the generic motion graphs that show objects with a jerk term, we have an example here that shows plus minus a with positive jerk. Of course, this object is moving to the right and it's slowing down, but it has a positive jerk term, which means the jerk and the acceleration are in opposite directions, so the magnitude of the acceleration is actually decreasing. We would immediately translate that into, because the acceleration is decreasing in magnitude, that implies that the net force is also decreasing in magnitude. Okay, so because it's plus minus a, the acceleration is negative, and again decreasing in magnitude. So it's below the time axis and approaching it from underneath. So again, because the acceleration is negative and decreasing in magnitude, so is the net force. Okay, we want to stress that whatever the acceleration of the object does as a function of time, the net force also does. Okay, it is probably important to remember that the acceleration follows from the net force, not any one particular force acting on the object. It is, of course, the net force, or the vector sum of all the forces. Okay, so we can imagine seeing any of these velocity or acceleration graphs and immediately translate those into what the effect is on the net force. Okay, so whatever the acceleration does, the net force also does, and of course vice versa. So okay, so we're going to look next at three-dimensional forces, IJK notation, and then we'll look at wind resistance and velocity-dependent forces. So that'll be all, and until next time, I will see you later.